Zooms, come on, this is muted, you see here.
Okay, didn't see that. Is everything okay now?
Could you minimize that?
Yeah, it's okay. Put the minus there.
Yes.
Yeah.
All right. So probing quantum gravity regimes in general is fairly difficult. And this is embodied in something called the cosmic censorship conjecture. So basically this conjecture tells us that all of the singularities all of the singularities are going to be covered by some sort of a horizon, or in other words, naked singularities cannot be observed. And so this is a cosmic censorship conjecture has been formulated some 50 years ago by Penrose, and it's believed to be broadly valid. It's been tested in many cases, but there do exist a couple of classes, so to say, that form an exception to this conjecture. And these cases, these classes can be broadly put in 3 different categories. So the first thing to note is that the endpoint of black hole evaporation already serves as a counterexample to this conjecture, at least on physical grounds. So what do I mean by endpoint black hole evaporation? I mean, the black hole evaporates and it shrinks down and eventually it reaches a Planckian size. And when it reaches the Planckian size, this is already the regime which we cannot explain within semi-classical gravity. So we have to go beyond it. And therefore, this is a naked singularity that forms. And also we know about theorems that actually prove this. They prove that if we want to go from something like a black hole to something like empty spacetime, this system must go through a regime of naked singularity. So this is one case. The second case is something called the critical collapse. The critical collapse here refers to the fact that we have some sort of matter that we want to collapse. And we can either collapse this matter slowly enough, so to say, without much energy, so as to just we try to collapse the matter and the matter just disperses away, so it forms Minkowski spacetime. Or with enough energy, we can collapse this matter into a big black hole. But we see that there's sort of a critical range of parameters for which we can tune them in such a way so as to form a very small black hole, so a Planckian black hole. So this, in the same sense, serves as a violation of the cosmic censorship. And finally, there is a Gregory-LaFlamme instability and Gregory-LaFlamme-like violations. And this is ultimately going to be the main topic of today's talk. But just in a nutshell, Gregory-LaFlamme instability refers usually to the ripping of some sort of horizons. So the usual case would be that we have some sort of a black string. This is the string that I was talking about. And this black string, that's for various perturbation parameters, so to say, can evolve into such a way so as to actually rip its horizons. So we're going to reach very small scales, and these small scales are going to be Planckian. And there's again a chat message. Should I pay attention to this? No?
No.
Okay. So the ripping of these horizons is in the same sense going to form a violation of the cosmic censorship. So ripping of horizons in this way is one example. Another example would be, for example, to take 2 black holes in high enough number of dimensions and try to collide them. You can throw them at each other, and for various parameters, for various values of the impact parameter, these black holes can come together, start to swirl around with each other, form some sort of a peanut shape, and then again disperse it. So when this peanut pinches off, this is where we expect the naked singularity. So these are all papers that exist that I can give you references for.
This notion is different than something like geodesic incompleteness, where like there's some point or a bunch of geodesics, and this is sort of a more general notion of singularity. Or
I mean, geodesic incompleteness is how we generally understand forming singularities, although they don't really tell us exactly that there's a singularity forming. They're just telling you there's some sort of a hole in the space-time. But
like
all of these singularities, sorry?
Is the pitching horizon an example of still geodesic incompleteness?
It's going to be forming a curvature singularity. So yes, in that sense, yeah.
Yeah.
All of these singularities that I'm referring to, in general, are going to be of a space-like type. So something that we don't quite know how to resolve within the current scope of string theory. So one might notice that all of these examples that I was talking about have something in common. And that something in common is that they are all, in some sense, very small. And more on this has been expanded in this paper by Roberto. And what do I mean by small? I mean that they have some sort of a cutoff onset, and they have a cutoff time scale that they last for. For me, it's a Planckian one. It can be a spring scale. It doesn't really matter what it is, but it's something that lasts for a very short amount of time. And so one can ask the question then, well, if all of these violations of the cosmic censorship are in this sense small, and they last for a very small amount of time, then isn't there some sort of a sense in which I have a modified cosmic censorship conjecture? Like a cosmic censorship conjecture tells me that naked singularities cannot be observed, but if only naked singularities that I can form are of this type, very small ones, then what is the sense in which I can actually probe those singularities? And that's a good question. And usually I wouldn't really know how to answer it, but thankfully, we do know one arena in which we can try to study what kind of signals will come out of these singularities. And this is, of course, the ADS-CFT. And so the calculation of this type has already been done in the case of the critical collapse. And this was done by Chesler and Way some years ago. And what I'm going to focus here in this talk is on these sort of singular signals that come from these singularities by looking at the Gregory-LaFlamme instability inside ADS. Okay. So first, I'll review some basics of Gregory-LaFlamme just quickly. I will explain a little bit about the tools that we use in order to actually evolve this Gregory-LaFlamme instability inside of ADS. This will use something called the large D approximation. I will, of course, show you the results of these approximations. And in the end, we're going to obtain the boundary signal. Okay. So let's recall what is the Gregory-LaFlamme instability about. So usually they refer to flat spacetime. And what the original paper considered is a 5-dimensional black string. So this is simply a Schwarzschild black hole put at each point on a circle. And of course, this is a system that we know how to compute its mass and entropy for. And one can ask a question regarding this black string, which is that this black string is an extended object. And one can ask themselves if this extended nature of the object is something that is always preferred. In order to answer this question, we have to go to the competitor of what this black string would be. And the competitor would be a localized spherical black hole. And we can compute the mass and the entropy of the spherical black hole, and then simply compare if there is going to be a phase transition between these two, which one is going to be preferred for what values of parameters. And it turns out that if we have thin enough strings compared to their size or length, the preferred configuration turns out to be the spherical black hole. So the extended nature is no longer the one that the string wants to be in. It wants to collapse down to some spherical black holes. So this is a thermodynamic argument, of course, we're just comparing phases, but this is something that can be verified through a linear analysis. And this is what the Gregory-LaFlamme actually did in the 90s. Finally, though, some 10 years ago, Lenner and Pretorius managed to verify this even at the full nonlinear level by evolving fully numerically this black string sort of wobbling and starting to pinch off. So this is how the Gregory-LaFlamme results look like. So we see here, we start with a black string, the time equals t0, and it evolves in time and starts to wobble a little bit. It starts developing these little blobs. And eventually it reaches this sort of a configuration in which we have these spherical black holes connected with very thin tubes. And the pinching of these tubes, that is to say this horizon, is exactly where we get the naked singularity from.
What is the color code?
Probably the mass distribution. Yeah, I would assume so, right.
I think there was something about them being self-similar and the tubes themselves then fractal.
We'll get there. Okay. So let me just emphasize again, what are the relevant parameters for this instability? Well, we have to take into account the length of the string, and we have to take into account the size of the string. And then we can form a dimensionless ratio of these two parameters, to sort of see an order parameter for this phase transition to occur. And this is in flat space. So what's going to change now if I put my system into a box, that is to say into ADS? Well, it's very simple. The length of the string simply gets replaced by the size of the box, that is to say the ADS scale. Okay. So what is the system then that we're going to be studying? We're going to study a black string in global ADS. Or more specifically, the system is going to have the boundary geometry fixed. And this boundary geometry is going to have two black holes at the antipodes of the sphere. So the system looks something like this. We see that at each z is the holographic direction. The metric is given by this formula. So at each z, at each holographic section, we have one black hole, and this extends all the way to the boundary. Some 20 years ago, Hirayama and Kang already showed through a linear analysis, so an analog of GREGORY-LAFLAMME, that this string has a tendency to be unstable. So again, for thin enough strings, we see a linear onset of instability. And now what we want to do in this talk is go beyond these linear perturbations. And this is something that we're going to do using the large D effective theory. So then what is this large D effective theory? So first of all, D stands for the number of dimensions. And this large D
There's a
approximation.
question on the chat.
Yes.
What is the difference between the GREGORY-LAFLAMME phase condition and the Hawking phase condition?
In what sense?
What is the difference? GREGORY-LAFLAMME, GREGORY-LAFLAMME is
I mean-
gravity, and Hawking phase is between gravity, the black hole and something else. So,
You're just comparing two different thermodynamic phases, and we start with two different systems in these two cases. The Hawking phase refers to transition between a black hole and a thermal ADS spacetime, whereas here we have either a string or two localized black holes. But the sort of principle behind it is the same. It's just comparing thermodynamic phases. Okay, so this large D approximation was introduced by Roberto and his collaborators as a way of effectively separating scales and isolating the dynamics of the horizon. So how are we supposed to think about this? So in the limit of very large number of dimensions, the gradients next to the black hole become very steep. So the potential is very much localized next to the black hole. And almost immediately outside of it, we have flat space. So we have a suppression of the gravitational potential outside of the black hole due to the very large number of dimensions. And so it's very clear that this suppression is going to introduce some sort of simplification to our equations. And this is basically the reason why we can perform these numerical analysis inside ADS within some reasonable amount of time. So let's see how we can apply this approximation then. We're going to start with the black string in some number of dimensions D. And I'm going to rewrite the metric that I showed you before in a slightly more convenient way. So here, it really doesn't look anything like convenient, but it's convenient for the purpose of taking the large number of dimensions, the limit of large number of dimensions. So what do I mean by that? We're going to have a set of rescaled coordinates. So Z, remember, is the holographic coordinate, and R is simply giving me the length, the size of the string. And we want to fix these two as we take the number of dimensions to be large. So what this means is that as I'm taking n to go to infinity, I'm taking z to be 0. So z equals to 0 in this coordinate patch means that I'm localizing to the center of ADS. So I'm localizing to the center. And for r, we see that r, the small r approaches r0. So we're localizing to the horizon of the black string. So we're going to the center of ADS and localizing to the horizon at the center. The reason why we do this is because the string is the thinnest exactly there at the center. And because it's the thinnest, then we can expect this GREGORY-LAFLAMME instability to occur there. So this very convenient metric implies a very convenient ansatz then. And it doesn't really matter what these equations and parameters mean. What is important here is this boxed set of equations, which basically represents the full set of Einstein's equations. These M and P are simply the nonlinear perturbations that we're imposing onto our solution. So remember, we start with the black string, we want to kick it in some way, and we're kicking it in a very nonlinear way. And these nonlinear perturbations are guided by these two equations. So this is basically the effective theory of horizons in ADS. And that's more or less all that I'm going to say about large D. So if you have any questions, feel free to ask them.
What do you say, nonlinear?
Nonlinear in the sense that we're not doing simply linear perturbations. We're not expanding in epsilon. We're really changing the metric in some.
So these are the full line transitions.
Exactly. Yeah.
So what was R0 again? Some couple?
R0 is the thickness of the string. So solving these equations, we can obtain many different configurations of the black string. But even before we solve the equations, we can see intuitively what kind of possible configurations can exist. So we can have something like droplets, some fat funnels, some droplets with a black hole in the middle, and so forth. But of course, we want to see what are the relevant phases. We want to perform the thermodynamic analysis first. So we want to compare, we want to see what are the relevant phases, basically. So let me just note for technical reasons that the thermodynamic ensemble we will be working in is the canonical ensemble. So this is because we basically have infinite n. The boundary black holes are fixed and they act as heat baths. Heat baths. They can exchange the energy with the CFT, or in other words, the CFT degrees of freedom are free to flow down the black hole and allow for an inflow of horizon generators inside the bulk. So this is something, this inflow of horizon generators is what we dub black tsunami, even though it doesn't make quite sense right now to call it a tsunami, but we will see later on why this is a good name. And of course, in such cases, because we're in a canonical ensemble, we have a sort of a free energy theorem instead of an area theorem. And for all the details about the system, one can go to this paper by Bunting, Fu, and Merrill. Luckily for us, Don and George already performed the detailed thermodynamic analysis for this setup. And among other things, their results indicate the following. So they see that uniform funnels, that is to say, usual black strings, are going to dominate when they're very thick. So this is very much analogous to the usual flat GREGORY-LAFLAMME case, where it doesn't matter how much we perturb it, it's very thick string, it's not gonna wanna go into any sort of other configuration. However, for thin enough funnels, they don't find that the droplets are the ones that are dominating. Instead, they find that fat funnels are the dominant solutions. So this is very much unlike the GREGORY-LAFLAMME case in the flat spacetime, where the droplets, well, the droplets would basically be the localized black holes. So this is interesting because naively, it would look like maybe there wouldn't be any naked singularities forming in this sort of a setup, given that I'm just starting with a black string and I'm ending up with an even fatter string. So there is no sense in which I can see where was any ripping of the horizon going on in the middle. Of course, this cannot be right because we know that if we zoom enough to the ADS center, we're basically going to obtain flat space dynamics. So the string is not going to see the ADS asymptotics. And therefore, we would expect the same type of singular pinching that one found in the GREGORY-LAFLAMME in space and flat spacetime. Sorry, this is a new computer. Okay, so let's now see how do we evolve these equations dynamically. So we go to the large C, we spent some minutes in Mathematica. So we basically start first with a black string, we perturb it in some way, and different perturbations are going to lead to different sort of endpoints of evolution. So one of them for sure is going to be going to the fat funnel. This is exactly what Merrill and Santos found. And if you want to see how this looks like in actual Mathematica, this is how it looks like. So we just see fattening of this funnel inside ADS. But of course, this is not the only possible endpoint. What we find as well is the expected pinch-off that I was talking about. Okay. So this is exactly the same type of dynamics that happens in flat spacetime. This is not the actual endpoint of evolution. This is just some middle stage. And from here, we can obtain several different endpoints, at least metastable ones. And one of them would be forming actual droplets as we expected them to form. And another one would be actually getting to the reason why we call this paper Black Tsunami. So why is this a Black Tsunami? Well, we can see it here. So it's a Black Tsunami because we have this pinching going on. And so the string started, it pinches off and starts to recede. There's these droplets forming. But then all of a sudden there's this huge impouring of the tsunami covering the singularity. And therefore, this is sort of analogous to what happens in tsunami-prone countries, I guess, where the seashore first, the seabed gets exposed first, and then it gets covered by a huge tsunami. Seabed here being the actual singularity.
What's being changed in the initial conditions?
So it's different type of perturbations that we're performing. So different parameters for the perturbations, but they're all sort of kicking the solution in some sense. So different functions, if you will, to put for M and P, that you're perturbing them in different ways. M and P are the actual changes to the metric that we're putting in, the nonlinear perturbations. So we're changing the metric in some sense, like G mu plus H mu, whereas the H mu is now not with an epsilon in front. So this H mu can take various forms, and some of them lead to, well, tsunamis, some of them lead to pinches off, and so forth. So just different types of perturbations.
I mean, to get the thing that's a direct tsunami, you just make the horizon get a little bit bigger and it just runs away, and to get the pinch off, you just squeeze a little bit and it runs down, or is it much more complicated than that?
One can say, let's say basically it's that, but it is slightly more complicated. These are the details that I guess I can show you later on if you want. Sorry.
So it looks like from your picture that there's just like one parameter which is like what fraction of the boundary black hole fills. I mean, that parameter in your solution, or
So the one parameter that we care about here is the ratio of the black hole size compared to the length of the string, that is to say the ABS bulk length. So we have to be in the regime where we know this is thin enough. And then we can perturb it in different ways, and these different perturbations are going to lead to different sort of evolution scenarios. Like in the reason why this parameter is relevant is for the thermodynamic analysis, but this is the dynamical evolution. So how do I get from different phases to one another? And for that, you need to perturb them in different ways. I can show you equations later on if that's going to help. Yeah. Okay. So this is sort of the bulk dynamical picture. But of course, we can ask a question: what would this look like from a dual perspective? And here I'm going to be very heuristic. There's nothing really that we can say except for one case that I'll follow up with. But from the CFT point of view, basically, all of these different phases are going to correspond to different Hawking radiation scenarios. Why? Well, it's because we have a black hole at the boundary. And this black hole is going to be filled out with some sort of radiation around it. So it's very straightforward then to sort of extrapolate what this would look like. The CFT picture of the black string is just black holes with some sort of a CFT halo around them. The tsunami, the fat funnel, is some sort of an analog of a large ABS black hole, and therefore corresponds to a radiation-filled universe. The pinch-off is interesting. It leads to some sort of a non-thermal burst on the boundary, and this is something that we will come back to. And these other two ones are sort of analogous to the previous two examples. So the thing that's interesting here is to know this naked singularity in the bulk having an actual CFT dual. So how can we see the pathological nature of the singularity on the boundary? Let me first note that large D is not going to help us in this case, given that large D is really the most useful approximation when we have horizons, so horizons and very low curvature. And here we literally have the opposite. We don't have any horizon, it's a naked singularity, and it's a very high curvature region. It's a singularity. Nevertheless, one can try to incorporate some sort of a large D approximation with 1/d corrections. And this is something that my collaborators have been working on. But there is a sort of a problem, basically because of this zooming in effect that I was talking about. So large D just zooms in into certain regions of space-time, Here we were zooming into center of ADS in order to study the evolution of the string. But of course, if I want to extract the boundary signal, I also have to see the boundary. Once we zoom in here, we don't really see the boundary. And so one will have to zoom out, zoom into the boundary, and then perform some sort of a matching procedure between the two. We want to extract the signal from here to the boundary. So this is all a little bit subtle and delicate. So that's why I'm not going to do it. Instead, what we're going to focus on here is a simplified setup, sort of a toy model for extracting the relevant signal that comes from this naked singularity. So this is very much a toy model, but I think these following assumptions do make a lot of physical sense. So what we want to focus on, basically, is the region very close to the pinch-off. So very close to the pinch-off, we're going to have very thin tubes going off to the boundary of black holes, but all around it, we have basically empty space-time. And if we're interested in extracting a signal, this signal can just propagate through this empty space-time, and it's not really going to care about this obstruction of these thin tubes that are around. So we're just going to throw them away all together and just approximate the space-time around the singularity as empty space-time. The second thing that we're going to focus on, at least, is the high frequency modes of our solution. So these are, of course, focusing on short distances, but more importantly, these high frequency modes are going to be sort of bullet-like propagating to the boundary. And so we can apply a linearized approximation to this actual propagation. So one might think that this linearized analysis is not really a good approximation, but luckily Chesler and Wei have already performed an actual full nonlinear evolution that showed that this linear analysis exactly coincides with the nonlinear results. So in that sense, we know that this is a good approximation. Finally, and crucially, we have to assume that our solution has some sort of a scaling symmetry. The scaling symmetry is known as self-similarity. The reason why we assume this is basically due to experimental, that is to say, phenomenological results. So we know from actually the first paper on critical collapse from Chapter, he saw this sort of self-similarity emerging as he was performing the naked singularity. We also know that fluid jet systems, which very much have the analogous Gregory-LaFlamme-like instabilities, have these self-similarities. This is what Nick was referring to. And therefore, it looks like the self-similarity is really a telltale sign of forming a naked singularity. And so we're going to make this assumption here as well. So let me just give you some sort of a basic intuition on what is this self-similarity telling us, actually. It's very simple. A self-similar function, about some point, is a function that satisfies a very simple scaling relation. It's f of t equals f of t times a parameter. Depending on the nature of this parameter, whether or not it's continuous or discrete, we're going to have continuous or discrete self-similarity of the function. For the purposes of maybe in 2 slides, I'm just going to mention one result, that this function that's scale invariant in one variable, for example, we can rewrite that variable as a log. And then the self-similarity over my original variable is going to be translated into a shift symmetry now. So we see here that f of tau, which is really a log, gets translated into f of lambda plus tau. So lambda is this parameter that tells me about the self-similarity. And now I can tell something a little bit more precise, which is that if my function is continuously self-similar, then that means that it's independent of this parameter in this log basis. If it's discretely self-similar, then it's periodic. Okay, so that's basically the setup. Or just to summarize it, we construct a self-similar solution of linearized gravitational perturbations around empty ADS spacetime. So that's what we're going to start. For now, though, I'm going to focus only on very simple observables, that is to say, one-point functions. So we're going to extract some sort of a stress tensor on the boundary. One should, and we will, study two-point functions and higher order functions, but not in this talk. Another thing that I want to mention is that I just want to sketch out the calculation that has been done. So for this reason, I'm not going to go through the calculation that we have done in our paper because that's very tedious. I'm just going to sketch out the calculation that has been done in Chesler and Wei. It's a much simpler calculation of this critical collapse of a minimally coupled massive field inside ADS. So just to repeat the sort of a logic, singularity comes from critical collapse, that comes from self-similarity. Therefore, we assume the fields around the singularity to have the self-similar form, and then we propagate away these fields up to the boundary. That's the basis of the calculation. Okay, so we start with ADS, as I said. We obtain a linear solution for a massive scalar, and this is a very familiar solution. It has some sort of a time-dependent part, it has an ADS part, it has a Jacobi polynomial part. And what I want to do is to choose these coefficients, A of n, in such a way so as to obtain a self-similar solution. So as I said before, we're going to focus to the center of ADS and try to form the solution to have the self-similar relation. So using some sort of asymptotic behavior of these polynomials, we obtain basically Bessel functions in the center of ADS. This is very correct, so to say, because Bessel functions are the ones that are relevant in flat space. So we're basically seeing just flat space in this center. But the reason why this is interesting is because now we see that our solution has this form where everything depends on nt and nx. And so we see if we now rescale t and x to go to with e to the lambda, we know what kind of a relation these coefficients have to obey in order to be self-similar. So this is how we obtain these self-similar coefficients in the center of ADS. Now we simply propagate this field up to the boundary. Boundary is going to be at some fixed x, and we simply read off the value of the operator associated to this field. And the result is the following. So this is the 1-point function of the CFT 1-point function associated to the field. And we see that basically we have this an, which is self-similar now. We have this sum function that only depends on nt. This t star is some sort of a constant, basically the time that it takes us to get to the boundary. And so what we have in total is a derivative of a self-similar function. And if this function is self-similar in a discrete way, then we know that it's a periodic function of a log. And therefore, the derivative is going to give us a divergence that goes as 1 over t. So this is the basic result that Chester and Ray formed, and they verified it through an actual numerical analysis. And what this tells us is that the signal is going to propagate away from the singularity. And when it reaches the boundary, once the signal reaches the boundary, this is when the singularity is actually formed. So what changes now if we try to do the same calculation with gravitational perturbations? Well, as I said before, the formalism is the same, the equations are slightly more difficult, but nevertheless, we can obtain the components of the stress tensor at the boundary. And the results are the following. So we see that the energy density and the pressures that I'm not showing vanish as we approach the boundary. We see momentum components are constant. And we see that the shear components have the same type of divergence that we saw in the critical collapse case of the scalar field. So this means that our boundary signal is not smooth. It's going to oscillate an infinite number of times before it reaches the boundary. Basically because it reaches arbitrarily high frequencies. So immediately now one can ask a couple of questions because we're basically forming a singularity that propagates to the boundary. So how does the CFT actually resolve the singularity? Well, we can't say anything right now, but the one thing that we can say is that because this energy density vanishes, and because the shears sort of diverge, this is very much analogous to how gamma rays behave. So these are going to be some sort of a gamma gravitons. They have very high energies, high frequencies, and they can go through you, but nevertheless, you survive. It's not that deadly for you. So what we believe is that in the same sense, these singularities that propagate up to the boundary are going to be in the same sense, not deadly for the CFT. Nevertheless, the stress tensor diverges. So does this mean that we cannot evolve past this time that it takes to get to the boundary? So at infinite n, it does really seem that we have the singularity and that's it. Like our stress tensor is singular and that means that we cannot evolve further. We don't have good initial data to build upon. But nevertheless, we see that, I didn't say this, but this expectation value of the operator goes as 1 over t, which basically goes as n squared. So it diverges because n diverges, n goes to infinity. So if we are to have finite n small enough, then we should have evolution beyond this critical time. We should be able to go beyond this critical time. And finally, can we predict the singular structure from some sort of a boundary calculation? Well, that's also very not clear. We give a prediction for how this operator expectation values are going to behave, but of course, one would need to do some sort of a matrix model calculation in order to actually verify our prediction. And this is a very difficult calculation that I'm not sure how to do right now. So let me just summarize. We saw that examining this Gregory-LaFlamme instability has led us to a variety of new results inside ADS-CFT. We have new phases that these black objects can exist in. For example, black tsunamis are not a thing that flat strings experience. And we also saw that this ADS setup allows us to have some sort of a boundary point of view to what's going on when this singularity occurs. So the main lessons that I want you to take from this is that the evolution leads to new dynamics inside ADS, but also cosmic censorship very much can be violated inside ADS. And this violation is going to be in the same sense small that I was talking about before. So there is some immediate future work that we are actually working on right now. So one can, instead of studying these black holes that are fixed on the boundary, we can move the boundary inwards and study them in a Randall Sundrum sort of a setup. If we do this, then we have an enrichment situation, given that if we have these brains allow for gravity, and so my black holes can back react to the radiation. And therefore, we can have evaporating black holes on the brain. And one dream that I would like to see actually realize is that one could maybe try to show that the naked singularity that would form on a brain would correspond to the Gregory-LaFlamme-like singularity from the bulk perspective. So what I mean is I have these wedges, these brains, of black holes. The black holes are going to evaporate. So from the brain point of view, they're going to evaporate completely, it gets smaller. From the bulk point of view, though, this is just going to grow into a bigger and bigger black hole. It's going to grow into a bigger and bigger black hole because I'm having a lot of radiation on the brain, and this radiation is dual in the same sense that a large ADS black hole is dual to some sort of radiation on the boundary. So that would be then interesting to see that this pinch-off would occur at the same point as the naked singularity that comes from the endpoint of evaporation. We don't have those results yet, though. If this would happen, then this would allow us to reduce the set of reduce the category of naked singularities to just one particular set. All of them would be of the same type, with the same sort of a self-similar structure, and we could be able then to say something about the endpoint of evaporation, which is, at least for me, very interesting. So that's some immediate future work, and of course, the very far away future work is the thing that I mentioned before, which is to study the formation of this naked singularity within a context of the matrix model. Because from the bulk point of view, this is not really something too difficult. It's just a bunch of gravitons and up on top of a vacuum. They just obey some sort of a symmetry. So one should be able to, in some sense, evolve this state on the boundary and see the same type of a structure appearing as we're predicting here. Okay. And so for my final slide, I want to show you an example of a real life black tsunami. Which is just a bunch of birds, really. Yeah, I found it to be quite interesting. So, thank you very much.
Thank you very much. Questions?
So you had this diagram of you had showed two possible scenarios for what happens in the evolution for the string. But before that, when you had the phase diagram that George and Maro had, they have this solution with the two droplets in the black hole in the middle.
That's also something one can obtain.
Oh,
I just show,
yeah.
One can obtain various things. All of the things that I showed as a phase solutions we can obtain them dynamically. It's just different types of perturbations.
Oh, okay.
I just emphasize the sort of say the most relevant phases that we obtained. The black droplets and the fat one.
So do they depend sensitively on the perturbation that you have? Is there some sense of chaos or is there a clear phase boundary?
Can you repeat the
That's-
question because I'm on online? It's not.
So the question is if the perturbations that we're kicking our string with are actually highly sensitive to the, are we highly sensitive to the perturbations that we're kicking them with? In other sense, is there some sort of a signature of chaos that would, I guess, you mean if I have chaotic system on the boundary that it would lead to deformation of this naked singularity?
Well, I just meant that depending on the perturbation, you get very different.
Yeah.
Does it get that sensitive?
I'm not sure what sensitive would be here. It definitely depends on that. But I don't think it's some sort of a fine-tuned example. But you can only in some sort of a fine-tuned way form a singularity in the bulk. It should be more generic than that.
The different phases that you have shown, do you think that at finite they're going to survive?
Yeah, of course. Actually,
Like the pinching singularity in particular, is that finite?
so, sorry, finite N or finite D?
Finite D, sorry.
Okay. So for finite D is actually where this pinching occurs. I was a little bit hiding things under the carpet. At infinite D, we never actually get a pinching in the sense that we literally see something pinching up. We always get these horizons to be very, very, very thin, get exponentially thin, and then they remain there as a sort of a regulator. This is simply because of the nature of
What is the scale?
the scale of what?
The minimum size?
It's some sort of a very exponentially small compared to the size of the black holes. So it's like geometrically different. And we know that once we get to these sizes, we already sort of went under the Planck scale, if you will. So we shouldn't truly trust it. And we know from other examples and from actual flat space Gregory-LaFlamme that there should be pinching. And so therefore we know that there should be pinching there as well. It's simply that large D effectively has this sort of a regulator action instead. But yeah, pinching should definitely be there at finite D. Yes.
When you get your largish black hole as the dominant, do you get pinching at the sides of that large?
No, it's going to be connected with these little tubes to the boundary. Yeah, exactly.
So you mentioned that the followers to CFT, so is it also CFT is large dimension or large dimension?
Sorry, I mentioned,
The CFT is also large dimension or?
my CFT doesn't have a large.
Yeah, you mentioned that it's a pure CFT. It's also
So-
large.
So the calculation that we did, the toy model calculation, is for any D. It doesn't require large D. So it can be in any D, I guess, greater than 4, to be sure. So the CFT is going to be correspondingly one dimension less.
So you have to consider like here you consider the large dimensional black hole. So in the CFT point of view also, you have to take a large D also or just some.
Well, so there's really two separate things that we do in this paper. One is a large D thing, one is an actual extractor in the signal. The signal itself doesn't require a large number of dimensions. It's actually more difficult with it. But the part where we do the actual evolution inside ABS, we do have the large number of dimensions, but we only focus on the classical dynamics inside the ADS bulk. So we don't really care about the CFT at that point. And of course, technically the CFT number of dimensions should also go to infinity, but we don't really care about it. We just want to extract the dynamics of the horizons.
Actually, what I want to ask is here in the CFT there is large and the large dimension and both are large. So how you scale? So that I wanna ask that, but
Okay.
that is not.
I don't think large D, large N CFTs have been studied before. It's an interesting question though, like how the limits would commute, not commute, in what sense, what can one extract? I'm not really sure, but it's a good question.
Any other questions?
I had mainly, this large tsunami, is there a way to see it as, because I have my boundaries are fixed. So there's an energy flowing in the bulk, because when my black hole becomes large, it needs some energy to grow, because the horizon area grows, the entropy grows. So can I think about it as some hoses which are connected to the boundary, and essentially putting boundary conditions on the ADS boundary to keep my black hole frozen, essentially allows me to, I mean, there's energy coming from the boundary
Exactly.
into the system to make the black hole large.
That's exactly it. That's why I mentioned that these boundary black holes are fixed and they act as heat baths and heat
It's heat bath,
sinks.
okay,
Exactly.
okay.
And this is infinite n dynamics. The
Mhm.
finite, at finite n, so it's a large n, but finite, you wouldn't have this infinite amount of import. You would have.
Can you put
attraction.
some boundary conditions to stop the flow and just keep, normally, you have a heat bath, so,
Yeah.
the temperature is kept fixed and, heat comes in.
Yeah.
But can you put different boundary conditions to keep, to stop the flow of energy towards the bulk?
I mean, the way that I would do it is to put instead these black holes on a brain, and that constrains the amount of energy that I can flow.
Oh, I
within
see,
itself.
because the brain is finite energy. Very good, very good. Very
Yeah,
good,
exactly,
Very good.
exactly,
It cannot come
yeah.
from anywhere. The
Yeah.
boundary is at infinity, has infinity. Okay, good.
Exactly. Yeah.
Wait, isn't what just is asking similar to putting maybe black droplets? The boundary, because they are technically a confined space.
I mean, black droplets in these diagrams that I showed you, if you start from a black string, I showed you that one of the endpoints is black droplets, but really that's not a thermodynamically preferred phase. It's a metastable phase. So eventually you are going to end up with a black funnel, which means stuff is going to start happening.
So the
again.
thermodynamics you do is not in the microcanonical ensemble.
It's
You are just-
canonical.
It's canonical ensemble.
Exactly.
So the heat is flowing
Yeah.
in, you're just looking at
Yeah,
the
it's canonical.
I see. So idea, I mean, so the idea, if you put things on brains, you could get finite energy, so you could go microcanonical and you could look at the phase diagram in the microcanonical.
And that's what we want to do right now. Yeah.
Nice, okay.
Any other questions?